I'm so happy to be here in Cardiff. It's actually my first time in Cardiff, so beautiful city, really happy to be here. And I'm the developer advocate in data science at JetBrains, so if you have any complaints or compliments about our tools, please do come to me. So today I'm going to be showing you some ways in which vectorized operations can help you speed up your data science code in Python, and I'm also going to pair that with an explanation of the linear algebra behind these operations. So if you're anything like me, when you first started learning to program, loops were your bread and butter. However, a lesson that I quickly learned, and the hard way, is that when you hit any sort of scale, loops get really slow. And initially, I was very new to programming. I didn't know how to deal with this. It wasn't until I completed a course in linear algebra that I was able to understand all this stuff I'd been hearing about Numpy vectorized operations and how I could use these to get those performance gains that I'd been looking for. So what I'd like to do in this talk is to give you an overview of a few different ways that you can use vectorized operations to speed up your data science code by iteratively improving an algorithm that I think a lot of you would have heard of called Canaras neighbours. So I chose this because this algorithm is based heavily on pairwise operations. And in my experience, these come up a lot in data science work, and they tend to be a massive processing bottleneck. So we're going to start by going over some basics of linear algebra, and then we're quickly going to go through how Canaras neighbours works. We'll then start with an unoptimized implementation of KNN, and that's going to be relying heavily on loops and lists. And then we're going to see how long that takes to run as our baseline. We'll then go through, hopefully if I can fit it all in, 3 different optimizations, at each stage taking out some inefficient part of the code and replacing it with something more efficient and vectorized. And as I said, at each stage, I'll be pairing the explanation of the mathematical principles behind them. So the most basic unit in linear algebra is a vector. So you can see here 3 examples of vectors. They're basically ordered sequences of values. So in the context of machine learning, vectors are used to represent data, and you can see that here. So on the right-hand side, I have an excerpt from a data set which I'll be using throughout this presentation, and it describes the physical characteristics of pictures of dried beans. It's a bit of a weird data set, but it had some really great properties for this analysis, so I just went with it. So what you can see is 2 of the columns, the major and minor axis length, and this is for 3 different beans. And what you can see is that each of the vectors represents a bean, with the first element representing the major axis length and the second the minor axis length. So what do these vectors represent in terms of linear algebra? For the purposes of this talk, we can think of vectors as coordinates in an n-dimensional space. A vector space, I should say. So to illustrate what a vector space is, let's start in 2 dimensions. It's always easiest. So we'll start with a scatter plot representing some beans against those 2 features that we just talked about. And this plot represents a 2-dimensional vector space with the major axis length representing the first dimension and the minor axis length representing the second dimension. And each of the points represents a vector in this 2-dimensional vector space. And you can see those vectors that I talked about in the last slide. So this beans data set that I'm using, it has 16 feature columns. And I can represent each bean as a 16-element vector, and it lives in a 16-dimensional vector space. So we obviously can't visualize that, but what I want to emphasize is that the principles that we can apply to 2-dimensional vector spaces translate directly to vector spaces with any number of dimensions. So now that we've covered vectors, matrices are pretty easy to understand. They're simply a collection of vectors from the same vector space. So you can see that we have 3 of our 2-dimensional vectors, and they all belong to the same vector space, so we can put them together in one matrix. Bringing this back to the dataset concept, this matrix is conceptually equivalent to our data frame, containing 3 bean data points with 2 columns. So Numpy represents vectors and matrices in a structure called an array. Arrays, unfortunately, have their own concept of dimension, and it differs slightly from what we've just been discussing in the context of linear algebra. So you can think of it as the number of sides in which an array can change length or size. So vectors are represented in a 1-dimensional array. And that's because vectors only ever change size in terms of the number of elements that they have. So you can see that here. You can see that this one-dimensional array will only ever change direction and that top dimension. And arrays also have a property called shape. And you can see that that's represented in a tuple, and each shape contains a number which represents the number of dimensions. So matrices are represented, unsurprisingly, in two-dimensional arrays. That's because we have information both about the number of elements and the number of vectors that live in that matrix. And then finally, a slightly more complex concept in Numpy is that of n-dimensional arrays. This is essentially a reshaping of one- or two-dimensional arrays so that they sit in a higher dimensional space. So you can see here that I took this two-dimensional matrix and I've reshaped it so it's now a three-dimensional object, with the first dimension now representing the number of matrices that that array contains. So let's just now briefly go over how k-nearest neighbours works. So a useful property of vector spaces is that vectors that are close to each other tend to be similar, and vectors that are far away from each other tend to be dissimilar. So we can see that in our vector space, those beans that are of the same type, represented by the same colour, tend to be close to each other, and those that are dissimilar tend to be far apart. So we're going to be talking about a way of measuring distance in vector spaces called the Manhattan distance. So to understand the Manhattan distance, imagine that in a two-dimensional vector space, you could only travel along the x and the y axes to get between 2 points. So I have these 2 points, A and B here, and say that I want to get between B. So I go boop, boop, 2 places along the x-axis, and then boop, boop, another 2 along the y-axis. So because I've traveled a total of 4, we have a Manhattan distance of 4. So we can also calculate that computationally by subtracting one vector from the other element-wise. And you can see that I've done that in this equation here, and we end up with that same result, 4. So we can generalize this to the Manhattan distance formula, which is the sum of absolute differences, indicated by that sigma sign, between all of the elements of two vectors. And again, like I was talking about with that 16-dimension vector space, while I've represented this in 2 dimensions, you can see that we can go up to n dimensions. So you can basically subtract 2 vectors of any size. So finally, let's go over how k-nearest neighbours works. So we start with a data set. We then divide it into a train and a test set. We take one test point at a time, represented by that orange dot, and we measure its pairwise distance between every single training point. So you can see we're already getting into a very expensive operation here. We then need to sort every training point by distance, and we retain the k-nearest points to our test point. So you can see here I've chosen 5 nearest neighbours. And then what we do is we get the labels of those nearest neighbours, and we just find the most frequent one. We then assign that label to our test point, and we repeat that operation for every single test point. So I think you can see where all the expense is coming in. So with this covered, let's move on to our first implementation of KNN, and we're going to time how long it takes. So unfortunately, because I can't see the screen very well, I've had to take some screenshots of the code, but obviously because I'm from JetBrains, I'm presenting it in one of our IDEs. So in this first function, we're calculating the Manhattan distance between 2 vectors. So what I want you to pay attention to is the input type. We're representing those 2 vectors as lists, and what you can see is that we have to loop over every element in that list in order to take the difference between each element. The next function applies this Manhattan distance function pairwise to every single combination of vectors between the training and the test data sets. So again, I want you to pay attention to the fact that I'm representing both the training and the test sets as lists of lists, and we're calculating those distances by doing a nested loop. The next function is designed to find the most likely label for a single test observation based on the closest training observations. So it does this by sorting all of the labels from closest to most distant to that test point, and then it calculates the most frequent label. And then finally, we have this function to bundle it all up. What we do is we run that function to calculate the most likely label for each test point over every test point. So you can see lists and loops galore. So now we've completed this first implementation, let's have a look at it with a few different data sets. So I've created 3 data sets to test this out. I have a small data set. It's very small. It only has around 4,000 observations, and it has 3 different features. I have a medium data set, which has 3 features, but it has a lot more observations. It has around 20,000 in the training set and 7,000 in the test set. And then a large data set, which is basically all of my data, and it has 16 features and that same 20,000 training and 7,000 test observations. So my idea about creating these 3 different data sets is I want to see the effect of increasing the number of features and increasing the number of observations on the time it takes this operation to complete. So let's see how we did. We can see that the training time is around 15 seconds for the small sample. This is a tiny sample. This is an extremely inefficient piece of code. We're up to 12 minutes already for the medium sample. And when we jump up to 16 features, we end up at 40 minutes. So why is this code so inefficient? So the first thing that we're going to talk about is what is the time difference? Like, why is it taking so much more time to calculate this on the large sample versus the medium sample? And the reason why is the way that we're calculating the differences between each element of the vectors. In order to calculate these distances, we're looping over the vectors and we're calculating the differences one by one. Because the large sample has 16 features and the medium sample only has 3, we see this consequent scaling up in the computation time. So the first thing we're going to do is get rid of this for loop. And let's jump over to looking at some more linear algebra in order to understand how we're going to do this. So it's possible to do a number of arithmetic operations on vectors and matrices. These include addition, subtraction, and multiplication. So obviously, for our purposes, subtraction is really interesting, and it's really straightforward. The way it works, as you can see in this diagram, is if you have 2 vectors or 2 matrices of the same size, you can line them up element-wise. You just subtract each element element-wise, and then you end up with a vector or matrix of the same size, which contains all of the differences. Something else you can do is apply operations to each element. So these all involve passing a vector or matrix through some sort of function, and then you just apply that to every single element. So the most famous of these would be scalar multiplication, where you multiply every single element by some number. But for our purposes, obviously, we're interested in being able to do the absolute value operation. So you can see how it works there. You just end up with a vector or matrix of the same size containing the transformation on each element. So let's use this knowledge to calculate our Manhattan distance a bit more efficiently. So the first thing that you'll notice is the input types have changed. I'm now representing them, like the 2 vectors, as Numpy arrays, not lists. And what this means is that we automatically can change the syntax completely. Rather than needing to do a loop, we can basically do this very elegant subtraction notation, and then we can apply the Numpy absolute function over that differences vector. So let's see how this improved our timing. So we're now down to 8 seconds for the small sample. All right. We're down to around 7 minutes for the medium sample, but the most impressive gain is for the large sample, as we predicted, where we're down to around 9 minutes from 40. If we look at the relative improvement in speed, for the small and medium samples, which again had 3 features each, we're around 1.8 times faster. But the large sample, as we've already noted, has the biggest improvement. We're more than 4 times more efficient just with this tiny change. But we still have problems. So the main culprit that's making our code inefficient is a nested for loop. I've already talked about this, that we're using to calculate those pairwise differences between every single train and test observation. So as we probably know, when we start nesting loops, the number of operations that we need to compute sequentially scales as a function of the product of the number of elements in each list, because we're permutating through every combination of those two lists. So this means that even with our teeny tiny small data set, we're running 3 million sequential operations to get the distances. And with the medium and the large samples, we pushed ourselves up to 140 million sequential operations. So this obviously makes the use of nested for loops really costly. So the second improvement is going to focus on how to get rid of this nested for loop, and we're going to replace that with something vectorized. So let's expand on what we know about vector subtraction to do this. So to start, let's imagine that we have 3 vectors, x, y, and z, and we want to find the pairwise differences between them. So this is what we've been using that nested for loop for so far. So let's start with getting the difference between each vector and the x vector. So one thing we can do that's more efficient than looping is we can use matrices. So on the left, we've combined each of the vectors into a single matrix, and on the other side of that subtraction, we've just replicated the x vector 3 times. So we can do it all in one pass. But the problem is we still need to repeat this for the y and the z vector, right? So we're going to have to loop. Well, this would be true if we were restricted to using 2D arrays like we have been so far. But fortunately, as we know, Numpy supports 3D arrays, so that means we can do everything in one pass. So let's have a look at a way that we might do this. We take our first matrix, the one which contains a copy of each vector, and then we reshape it so that it's now a 3D array. So we have one copy of that matrix sitting in the first dimension. We then replicate it 3 times so that we end up with a 3 by 3 by 4 3D array which contains 3 copies of each of those vectors. We can do something similar with the matrix containing 3 copies of the x vector. We again reshape it so that it's a 3D array. Then we do the same thing with the x vector and the same thing with the y vector, squash them all together to the same 3D array, and then we have, again, a 3 by 3 by 4 3D array. So we can just do a straightforward vector subtraction because each element lines up along each dimension. Great. Problem is, though, we're now explicitly replicating our vectors multiple times, and this is pretty inefficient. Luckily, Numpy can help us here with another trick, and this is called broadcasting. It's probably something that a lot of you have heard of. If you haven't, it changed my life. So this is essentially a memory-efficient way for Numpy to do the sort of operation that we just did without the need for explicit replication of the vectors within the array. So the way that it works is if we want to do an operation that has 2 arrays, Numpy first compares to see whether they have the same number of dimensions. If it does, the next thing it checks is, do the size of those dimensions line up? If it does, then it just goes ahead and completes the operation as usual. If it doesn't, it checks whether the size of one of the mismatched dimensions is 1. If that's the case, then it will stretch or replicate the size of the smaller one so that it matches the size of the bigger one. So I'll show you explicitly how it works with our little example. So we take our original matrix, the one that contains 1 copy of each vector. So on the top, you can see that I've done that same reshaping so that we have 1 copy of that matrix sitting in the first dimension. Down the bottom, we do the same thing, but this time we reshape it so we have 1 copy of that matrix sitting in the second dimension. What happens if we try to do a vector subtraction between them? Well, Numpy is going to do that comparison to see the size of each dimension. And it's going to see that the size of the first dimension has 1 in the first array, and in the second dimension it has 1 in the second dimension. It will then stretch out each of those arrays along the smaller dimension so the sizes match, and when it returns the value of that subtraction, it will essentially be a 3 by 3 by 4 array containing all of those differences. So let's have a look at how to implement this. What you can see is I've made some big changes here. Rather than having 2 separate functions to both compute and to implement the Manhattan distance, I have a symbol function that does both. So what we're doing is we're passing in all of the train observations and all of the test observations as 2D Numpy arrays. In this first line, what we're doing is the broadcasted subtraction. So this slicing notation that we have is recasting them as 3D arrays. Where I have none, it assigns a size of 1 to that dimension. And so just like with that example in the previous slide, it's going to stretch out each of those arrays so they're the same size for that subtraction. It'll do everything in one pass. We end up with a 3D array containing all of the differences. We apply the absolute value function over it and then sum them. And so that does the exact same thing we did in two different functions in one pass. Sorry, got the hiccups. So how did this go with our computational efficiency? For the small data set, we're now down to 1.5 minutes. We're down to an astounding 1.5 seconds. We're down to astonishing 1 minute for the medium and 3 minutes for the large data sets. So we check this as a factor of our baseline implementation. All the data sets are now running between 10 to 13 times faster. So we've gotten rid of the biggest bottleneck in our code, but there's one additional improvement we can make, and I hope I have time for it. So we haven't touched the KNN code. That's still in lists. So let's see what we can do here. If we have a look at this function for finding the test points nearest neighbours, the most expensive operation that we have is a sorting of the entire training set distances. So essentially, this is a sorting operation. Sorting operations are expensive. We then have this second line where we iterate over every single observation in the training set in order to extract the labels. So why is this a problem? Sorting lists in Python is locked to just one sorting algorithm, timsort. In contrast, Numpy sort and argsort, the two methods, have more flexibility. So when you don't specify a method, Numpy sorting defaults to the faster quicksort. And even when you select stable sorting, the algorithm that you use will be adjusted to the data type of the array. And then, of course, one additional issue we have is that list comprehension, which is just a for loop by another name. So the major change that I've implemented here is in the second line down. So essentially you can see that I'm applying argsort to each of those distances to a particular test point. I then, at the end of that line, use a slicing notation which just keeps the column of a 2D array which contains the distances and the labels. And instead of having to iterate over every single element to extract the label, I just keep the column containing the labels, and it's much more efficient. So how did we go for time with the final optimization? We're down to 13 milliseconds for the small data set, 15 seconds for the medium, and 2 minutes for the large. So when we look at our final timings, we managed to get around 15 times faster for the large data set, 50 times for the medium, and surprisingly to me, over 1,000 times faster for the small data set compared to baseline. So these are quite impressive gains, but from reading around on this topic, it's pretty typical to get these sort of gains when you implement vectorized operations rather than lists. And that's it, I made it. So I hope this gave you a grounding on why NumPy's vectorized operations work the way they do, where it can be helpful to apply them, and maybe where it's not so helpful to apply them. So you can see my Twitter handle and my blog. Please feel free to reach out, and thank you.